Physics 1. And now, here's your professor, Varanga Pereira.
Hello everyone, welcome back. So we've been recently talking about Newton's laws, and so we'll continue doing that for the rest of the week, leading up to the midterm on Tuesday. More on that later today. We'll send out an announcement about the midterm, what to expect, also some practice, additional practice, in addition to the homework you have, right? Homework 1 and 2. We'll have a little bit more practice as well, right? So come to drop-in hours. If you have questions, don't hesitate. Monday through Friday, right? So we're available on Zoom. Come talk to us. Happy to help. All right, so looking at the slide here, I'm going to show you a picture from Apollo 12. This is Pete Conrad. He's the third person to walk on the moon. And this is what he said when he landed on the moon, right? So let's take a look at the video, and we'll talk about what all this has to do with Newton's laws.
You're coming into the picture now, Pete. Okay. Okay, got the old camera running. Okay. Down to the pin. Okay. Man, that may have been a small one for Neil, but that's a long one for me.
So going to the slide here, you have the quotation here of what he said. If you couldn't make out, it's a little mumbled with the audio. But this is what he said. Whoopee, man, that may have been a small one for Neil, but that's a long one for me, because he's kind of making fun of the fact that, well, Neil Armstrong had the one small step for a man, right? So that quote, he's kind of making fun of it a little bit, because after Apollo 11, there's a lot of people saying that Neil Armstrong kind of had those words kind of polished and told by NASA to say that, right? So somebody kind of wrote that for him, but Neil Armstrong always maintained that he just made it up, right? At the moment, that's just kind of what came to mind, and that's what he said. But it seemed a little polished and seems nice kind of statement. So then a lot of people were skeptical about it. And so by the time the next mission came along, Apollo 12, reporters were asking the next person to land on the moon, Pete Conrad, you know, let's be honest, like tell us the truth that somebody actually told Neil Armstrong to say those things, right? And then the point was no. And so to kind of prove that, what Pete Conrad said was well, why don't we agree about what I'm going to say on the moon when I get there with the reporter. And this was what they agreed to. And so once he got to the moon, he just said exactly that. And they had a bet, and apparently he couldn't never find that reporter again to settle the battle. So why do I bring this up? Because we want to start talking about weight, right? So Pete Conrad may be slightly smaller than Neil Armstrong. So mass and weight, these are words, again, that we may be using in everyday life interchangeably, but we have to be really specific when it comes to physics, right? The mass means something specific, weight means something specific. And then we'll finish off Newton's 3 laws. We'll talk about the third law, right? So there's a homework problem or two that involves a couple blocks. So you need to consider the third law to solve problems that involve contact between multiple objects, right? So we'll finish that off. That gives you the full set so that you can do all of the problems associated with Newton's laws of motion, right? Okay, so to get us started, let's look at this demo video on how to measure weight, right? So, and then that'll get us thinking about that, and then we'll talk about kind of the more mathematical form of it. So let's take a look and we'll come back. In this demo, we're going to talk about weight. So you can use a scale like this to measure weight. Hang an object down here, and you can just read off the scale. This one's going to measure in newtons. So behind here, you can't really see what's going on, but what's happening is you could have a spring like this and connect it to an object, and then you can tell the weight of that object by how much the spring is stretched. So the heavier the object, the more the spring will stretch. And so by that amount, you can tell the weight of an object. So that's a way to measure weight. So you can see that in different scales. So there's a slightly different scale. Again, an object held here, and you can just go off and read what its weight is just by looking at the scale here. Another thing we can do is take this object, connect it to this scale. Now, you'll read the weight, right? So you'll see 10 newtons or so is the weight of this object. But what if I accelerate everything up or down, right? So the scale as well as the object, if I accelerate up, it will read a higher weight. So it seems to be heavier than it is if it's stationary like this. And the reverse is also true. If I were to drop the whole thing, then it would measure a lower weight. So if it's actually in free fall, then you wouldn't be able to measure a weight on a scale like this. So that's weight and how to measure that using different scales. Okay, so let's talk about what weight is, right? So we'll start with Newton's second law in the case where mass is constant, F equals ma, right? And it's just this, right? F equals ma. We're just giving a name to one of the forces. Now, when you write F equals ma, it can be any force, right? So it's a general idea. It doesn't have to do with gravity. It could be a spring. It could be you pushing a box. So the force in F equals ma is a general force. But in the specific case that, let's say there's a box, right? And then there is a force that the Earth is applying to the box, right? Because if you hold the box out, let go, that force, you can see the effect of it by the box falling to the ground, right? So that force of gravity, we're going to call weight. Okay, that's all it is. We're just labeling this force as weight, okay? So that means you can write F equals ma as this weight is equal to the mass times the acceleration that's specific to the falling object, right? On Earth, you put 9.8 meters per second squared, but that g is really a, right? We're just kind of, it's still F equals ma, but we're just labeling things a little differently, right? So again, force, standard units for force are newtons, right? Standard units for mass, kilograms, and then standard units for acceleration in meters per second squared, right? So weight is in the units of newtons, right? So in the US, in a lot of things we're dealing with pounds, right? It gets a little confusing. If you're interested in kind of how all this fits together with that system of units, go ahead and look that up. I'm not going to really talk about it because it just makes things really confusing. So it's better to stick to the SI system, right, generally. So in the SI system, the weight is measured in newtons. Any force is measured in newtons. That's the standard unit, right? So if you take 1 kilogram, right, so 1 kilogram of apples, right? Okay, so what does that mean in terms of its weight? That means it's 9.8 newtons, right, is its weight. Okay. Okay, so let's try this out for yourselves just to get the hang of all how weight, mass kind of can be worked out using a problem. Let's go to our Instapoll here. I'm going to send this your way. There'll be a thread on Add Discussion just for Instapoll 1. If you have questions about that, so take a look at this. Let's pause for a minute and a half, have you take a look at this, and then we'll come back. Okay, any questions, Jericho, yet? Okay, Jericho's here monitoring the ed discussion. Ask questions if you have questions. Okay, let's see. Okay, responses coming in. So when we say who is richer, right, what do we mean by that, right? Do we mean the weight? Do we mean the mass, right? Like if you're talking about gold, if you took some gold to trade for dollars, let's say, how would you have more or less? Like what does that mean in terms of the gold, right? So you want to think about that. Okay, let's see, kind of where are we roughly standing here in terms of distribution? Okay, kind of a tie actually, so roughly distributed between your friend and you. Some are egalitarian, or both are equally rich, that's good. All right, so which is it? Which of the options is this? So let's go to our notes here and try to work this out. Okay, using the ideas of weight, right? Weight and mass. Okay, so we will write down weight is the mass times the acceleration due to gravity, right? And when we're doing a comparison, you can write that same equation twice, right? So because what we have is we have a weight on Earth that's equal to the mass on Earth and the acceleration due to gravity on Earth. We're comparing two things, right? The Earth and the Moon. Then we have the weight on the Moon is equal to the mass on the Moon, of the gold, of course, right? And the acceleration due to gravity on the Moon, right? So we did that calculation earlier. So when we write this, what's the same? What they give in the problem is that they tell you that they just won a Newton of gold in the context, right? Contents, and then you did the same, right? So you won the same amount, right? So in terms of the weight, you both have 1 Newton, right? So that's the similar value. Once you know that these two are equal, what you can do is to say, okay, I'm going to set that equal to each other, right? So because this is both 1 Newton, I can set these two to equal to each other and say the mass on the Earth, acceleration due to gravity on the Earth is equal to the mass on the Moon, acceleration due to gravity on the Moon, right? I'm going to set that as an equality. And now I can see what's going to happen in terms of the mass of the gold, right? So if you're richer, you mean you have more gold in mass, right? The mass, the stuff of gold you have more of. So let's see if which is which. Now, what we're going to do is focus on the acceleration, right? We have some idea of what these numbers are, right? So the acceleration due to gravity on the Earth is 9.8 meters per second squared. And then we saw earlier that the value on the Moon is 1.6 meters per second squared, right? So for this to be equal, if this is a small number, this is a large number, what does that mean in terms of the other two, right? The mass is what must be true, right? If you just have, this wouldn't work, right? This is not equal to this, right? So for these two, the left-hand side and the right-hand side to be equal, what must be true, right, between these two, the mass is this one. It needs to be a larger number, right, to compensate for the fact that this is a smaller number, right? So a larger number multiplied by a smaller number can be a smaller number multiplied by a larger number. That could be equal, right? So what does that mean in terms of the who's richer? Yeah, the quantity on the Moon is larger, right? The mass on the Moon is larger of the gold. So who, you or your friend, is richer? Oop, gotta zoom out here. So switching back to the slide here, there we go, right? So your friend is richer, right? So you kind of see that changing here, right? Does that make sense? Okay, so ask questions on a discussion if that makes sense, right? So you can reason using equations, right? Anything popping up yet? Okay, cool. All right, how about we try another one? Okay, zoom into this. Maybe that's a little too much. There we go. Okay. So have you work on this? Maybe take a minute and a half as well. And we'll come back and talk about this. Okay, let's see. Answers coming in. Try to get your answer in to see. It's good to try it out. If you're not sure, no problem. Just try it out, and we can talk about what that is. Make sure you're drawing pictures, right? A lot of text here. So let's see. What are we getting? Okay, stayed the same, increased, right? So kind of roughly. Stay the same is the most popular answer. Increased is the next popular answer. Okay, so let's switch to our notes and try to work this out. So answer poll 2. Okay, let's draw a picture, right? So here's a good case where you should draw a picture. It helps. A stick figure is perfectly fine. Here's our elevator. You can draw kind of a bathroom scale kind of thing right here. And then you can put a person, a stick figure of a person, right? And what is the problem saying, right? So you're in an elevator and it accelerates upward. So let's put that information too. So it accelerates upward like this. Okay. And what's going on in terms of the scale, right? So we want to think about the forces. What is the scale doing? What is our big idea? The big idea is that the sum of the forces equals mass times acceleration, right? So here's a case where there is acceleration, right? So you, the person, is accelerating, right? So let's think about the forces involved, right? So what are the forces involved here? The person clearly has a weight. Right? So here's our weight. And what else is acting on the person? Is it just the weight? All right, so what else is acting on the person, do you think? Right? Is just gravity pulling down? What else is there, you think? What's the surface of the scale doing? It's applying a force, right? So there's a force on the person, right? The scale is applying a force upward like this, right? So if we focus on the person, right, how the person accelerates and things like that. So we're focused on the person. What are the forces acting on this person? There is a weight of gravity pulling down on the person. Then the surface of the scale is also pushing upward on the person, right? So when we're summing up the forces here, what we should do is have this force, it's the normal force, right? So it's called a normal force because it's 90 degrees to the surface. Well, more on this later. It doesn't particularly matter right now. But the normal force, or the force that the scale is applying upward, is there. And we have the weight, right, of the person due to gravity. And we set that equal to ma, right? So I'm going to drop the notation of vectors because it's only in one dimension, right? So if you use our x, y coordinate system, it's only in the y direction. So I'm going to drop the vector notation because it's very clear what direction negative means negative y, right? So positive here means positive y. If we solve for the normal force, right? Notice that the normal force would be larger when there is an acceleration, right? So imagine there was no acceleration, right? So you can just get rid of this term. If the elevator was not accelerating, the normal force and the weight, right, of the person would be the same. If there is an acceleration, right, then the normal force will be a larger number, okay? So that's the interesting thing about a scale is that this, right, this normal force is what you're measuring as your apparent weight, okay? So your bathroom scale is indirectly measuring your weight. It's not directly measuring your weight, okay, which is maybe not obvious, right? When you get on your bathroom scale, you measure your weight, right? The end. And yeah, that's true as long as you're not accelerating, right? Because if you're not accelerating, then what's happening is that, oh yeah, if you're not accelerating, then the normal force and the weight are the same, right? If you're accelerating, that's why this bathroom scale is going to read a larger number, right? Because the apparent weight is going to be larger. And similarly, if you set this to be the opposite, right? Let's say the elevator is falling, right, at the same rate as 9.8 meters per second squared, then that would be a negative number that cancels with this, and then you can get a normal force to be 0, right? So thus the quote-unquote weightlessness, right, that you would experience. Does that make sense? Okay, is there questions about that so far? So going to, let's see, what did I do with the polls? There we are. Going to our poll here, what is the answer though? Still, there's a split. So thus you have the tactile measure of evidence, your weight, right? What has happened to your weight? Why stay the same?
Because the scale is reading the normal force
Yeah.
rather than your weight.
Right. Other ideas on that discussion? What do you think it is? So something increased, something stayed the same. What increased? What stayed the same?
The normal force increase?
Yeah, normal force increased, right? That makes sense? Any questions on a discussion? No questions? Okay. So going to our notes here, right? When I say weight, right, this is what I mean, right? This is your weight. That's how much the earth pulls you down. How much the earth pulls you down, we saw earlier, right? You can get by taking your mass and multiplying by the acceleration due to gravity on earth, right? So your mass doesn't change, right? And then as long as you don't get too far away from the earth, if you're just on the surface of the earth, that's a constant number as well. So then these two together, that's your weight, and that doesn't change, right? So the tricky part is with the elevator and a bathroom scale is just like you saw in the demo, you're not really measuring this directly. That's the issue here, right? If you were just directly measuring your weight, then it's the same, the end, and no problem. But the problem is that if you get on an elevator and it's accelerating and you're on a bathroom scale, because the bathroom scale is indirectly measuring a weight, it can be kind of thrown off a little bit, right? So the apparent weight can go up if you're accelerating up, and the apparent weight can go down, decrease to zero at a certain point if you're accelerating downward, right? So that's why when we talk about weightlessness, it's a little tricky. So when here, let's go to our slides here, right? So you'll see the word weightless. That's a little kind of funny kind of phrasing, right? So if you say that these astronauts on the International Space Station are weightless, they're not, right? They're not weightless, right? They're apparently weightless, right? The apparent weight is zero because they're accelerating downward constantly, right? So just like if you've been on a roller coaster, or there's sometimes in the elevator it kind of drops momentarily, right? It's certainly in a roller coaster, when you're kind of go up, and then that moment you're coming down, you feel like your stomach's kind of going up and it feels kind of strange. That's what they're feeling all the time, right? That feeling of weightlessness is an apparent weightlessness, right? Because these people still have a mass, there's still an acceleration due to gravity here, right? At the International Space Station, there's a value for g, which is slightly smaller than 9.8. So they have a weight here, right? All three of these astronauts, they have a weight, right? It's just that if they, at this moment, got on a bathroom scale, it would read zero, right? Does that make sense? Okay, so just be careful with the phrase weightless. It is, it's better to say the apparent weightlessness, right? And because it's just the way you're measuring this. Okay, are we good with that? Weightlessness, weight, mass?
There's some confusion between the scale reading the weight, apparent weight versus the weight.
Yeah, so what the scale is reading? Yeah, so the way that the scale works, right? So if you go to our notes, like how does a scale work, right? Think about a scale. If you open up your bathroom scale, right, here's your scale. What's inside? Roughly, let's say it's a spring, right? I'm just kind of roughly mimicking what a bathroom scale is, right? So, but more obviously, if you go to the grocery store, for instance, and you're trying to buy produce, then that scale is more or less like a spring. You might literally be able to see the spring behind it, right? So if you have a spring, right, and it's unstretched, it might read, okay, 0, right? The scale, when the spring is unstretched, might read 0 newtons, right? Does that make sense? Now, if you step on the bathroom scale, right, and it's compressed, maybe slightly, right, and the spring is now compressed, it might read, okay, what is it, 100 newtons, right? And it's that compression that reads that number, right? So think about what's happening to the scale when let's say we'll put a ground here, right? Here's the ground, right? And we'll assume there's a person, feet of a person, right, standing on the scale. It's the compression that reads a number, right? If it's not compressed, it won't read anything. So in the case of just, let's say you're not accelerating, you just not on the scale, you're on the scale. What's happening in terms of the spring, what's being pushed? So from the top comes the weight of the person, right? That's what's being pushed down. From the bottom, right, what's happening there, right, at this point is the ground, the force of the ground pushing, right? The ground is pushing back on the scale, right? So that two forces together, right, compress that spring. Does that make sense, right? So that's what I mean. So the reading of the scale has to do with this compression process, right? So imagine if you got rid of this floor altogether, then if you got rid of this floor, there wouldn't be this force here, and that means you couldn't compress this spring. Even if somebody was standing on top of it, right? The whole thing would be constantly falling because there's no way to push back and compress, right? Does that make sense? So that's what I mean. So that's why when you look at a bathroom scale, that compression process, right, is dependent on what the floor is doing, right? If the floor is staying put, then that's fine. That's kind of easy because, okay, the weight pushed down the same. So if it's 100 newtons from the top, it will be 100 newtons from the bottom, and then they compress, and then it reads 100 newtons. Great, right? But in the case of the elevator, what's happening is that the floor itself is accelerating upward, right? So there's a greater force than this weight, right? For the bathroom scale to accelerate, it has to have an imbalance of forces. So then the force from the ground is much larger, right? So it's going to compress the spring more, right, than it would have had it just been used scanning on the ground, right? Does that make sense? So it's just the mechanism of how the scale works in reality, right? That's what it's really that number that you see on the bathroom scale is an apparent number because it's really measuring some other force that's a proxy for your weight, and it's a very good one, right? It works as long as the ground doesn't accelerate on you, right? So as long as you're not on an elevator, for instance, normal force and the weight will be the same. Right? Does that make sense? Hopefully that clears it up a little bit, right? So just kind of think about that some more because it's important to distinguish, right? So the weight, right, is just the force of gravity pulling you down, right? It is independent to how you're actually moving at the moment, right? If you're accelerating or not. The weight is there's a certain force acting on you, right? But how that's measured, right, is an indirect process, and you can kind of see that that you normally wouldn't see if you're just getting on a bathroom scale, right? You wouldn't really necessarily see that. Okay, so one other thing we want to talk about before we get back to doing some more problems is the last of Newton's 3 laws of motion, Newton's third law. Okay, and in terms of equations, it's written as this: the force that A applies on B is equal to the negative of the force that B applies on A. Right, so in words, you might have heard of Newton's third law as every force has an equal and opposite reaction. Right? So the opposite part's the negative. This is a vector. It points in a certain direction. So the negative of that vector, right, is what it's saying. It's the opposite. Same magnitude, right? This vector and this vector have the same length, right? So every force has an equal and opposite reaction, right? So if you push on something, let's say you push on a wall, let's say force AB is you pushing on the wall, there's going to be an equal and opposite force that the wall applies to you. Okay? And you can go as far as to say that you cannot apply a force larger, right, than you can get a force back from something. Okay? So the kind of this example is with a piece of paper. Take a piece of paper and punch it as hard as you can. If you punch it as hard as you can, there's no amount of force that you can apply that's larger than the paper can push you back. Right? So you might think, well, I'm much stronger than a piece of paper. I'm going to punch the piece of paper really, really hard. No matter what you do, the force that you put on that paper is equal in magnitude to the force that the paper puts back on you. Right? So in the case of the paper is fairly weak, so it's not going to actually hit you very hard. But this will work on an actual wall as well, and so don't recommend you do that, because if you punch a wall, it will hit you as hard as you hit it, right, in exactly the same way. So, so you don't want to do that. Going to our slides here, a good example of Newton's third law in action is a rocket. So this is the Saturn V. This is the rocket that took astronauts to the moon. And what this is doing, it's saying that, okay, what's the force that's being applied? What's the reaction? And it has to do with all this stuff coming out of the back of the rocket. This is the exhaust, right? So once you burn the fuel, there's all these hot gases that come out of the rocket of the back. So the first force is the rocket pushing all this material out the back. Right? So all this stuff is in the rocket initially, right? The propellants. When it combusts, all these hot gases get shoved out of the back of the rocket. That's the first force, right? The force that pushes all this stuff out. And the reaction is that the exhaust pushes on the rocket forward. Right? And that's what propels the rocket forward. That's why you can still do rocketry in space. Right? There was a misunderstanding earlier, 100 years ago, about, well, you need something to push against. So if you're in the vacuum of space, you couldn't go use a rocket. But a rocket doesn't need air around it, right, to go through. You can work very well in space because what's being pushed is the exhaust, and the exhaust pushes back on the rocket. So it's kind of, that's what makes the rocket move, right? So one of the key things about Newton's third law is the two forces apply on two different objects, right? So the equal and opposite reaction, don't put it both on the same object, right? So if I go to the DocCam here, if I have my pen, right, and I have it on the notes here on my piece of paper, if you think about, okay, what's the equal and opposite reaction to the pen, we know that the pen has a weight, right? So that is acting on the pen. We know there is a force that's being produced by the table that's holding the pen up, right? So think about what's the equal and opposite reaction. If you're looking at the weight, right, that the earth pulls down on this pen, the reaction is that the pen pulls on the earth, right? So the two forces are on two different objects. It's not on the same object, right? So when you have the weight of the pen that's acting on the pen, and you say, well, the reaction is the normal force, right, off the table, notice that you're talking about the same object, right? The normal force is acting on the pen, the weight is acting on the pen. That is not the equal and opposite reaction. That's not the third law, right? That's not what it's talking about. So if you're applying the third law, just be sure it's different objects, right? So if you're talking about the normal force that's acting on the pen, right, the table is pushing up on the pen, then its pair is the pen pushing down on the table. Right, so they're acting on two different objects. So just be careful. It's a somewhat of a simple idea, at least seemingly, right? But when you're actually applying it, just be very cautious that you're applying it to two different objects. If you're pushing on the wall, you on the wall, it's wall on you, right? So you pushed on the wall. The acting object is the wall. then the wall pushing back on you, the acting object is the force is being acted on you, right? So it needs to be on two different objects to have the equal and opposite, the pairs of forces, right? Okay, questions about kind of the more recent things we've talked about? Give you a second to put your questions if you have them. Question?
You said that if the pen is being pushed down by gravity, you
Yeah.
can't say that the normal force is normal force on the pen, or the third law of Newton's, because
Yeah.
it would be the same force.
Yeah. Well, it's different forces, but it's acting on the same object, right? So let's yeah, that's a good point. Let's think about the pen example, right? So here's our pen. If it's resting on a table, if you're focused on the weight, right? So if you're talking about the weight of the pen, what does that mean, right? So weight, what's pulling on what? The earth is pulling on the pen, right? So the pen is being pulled down by the earth, right? So that's one force, right? So let's say the force that the earth on the pen, okay? Now its reaction, right, is that if the earth pulls down on the pen, then the pen itself is going to pull up on the earth, right? So I'll say its reaction, so the force that the pen applies on the earth. Use the equation here, there we go, and say that's negative. This seems, maybe it seems a little odd, right? Because it's more obvious when you say, okay, clearly if you hold a pen out and let go, the earth clearly is pulling the pen down. But it's less obvious that the pen itself pulled up on the earth at the same time, right? Because the earth is very massive. You don't notice that it did that, right? But if you go deep in space somewhere and you had something that's two equally massed objects, then you'd see more of an apparent effect of this, right? That the two, because they're pulling in on each other, both of them would significantly accelerate towards each other, right? But the Earth is extremely massive compared to the pen, so the Earth does accelerate upward by almost not, like very little, right? You wouldn't be able to even measure it, right? Because it'd be so small. So that's the equal and opposite pair here, right? It depends on the force, right? What are you focused on to find the pair? So if you're particularly focused on the weight of the pen, where's that weight coming from? The earth pulls on the pen, right? That's where the weight is coming from. Then these are the equal and opposite pairs. Now, on the other hand, you might say, okay, I have the pen, and I want to talk about the table, right? I want to talk about what the table is doing to the pen. Okay, clearly when the pen's on the table seems to push up, right, on the pen, because if it didn't, it would fall, right? It would go through the table. So that force, again, we'll talk about why it's called a normal force later, but it's called a normal force. Use the symbol N here. So the table pushes up on the pen, okay? So now notice here, it's on different objects. Earth on pen, pen on earth, right? The forces are acting on different objects. So if you have this situation, then now what we have is the force that the table is putting on the pen, right? That's one of your forces. Now, okay, table on pen, that means pen on table, right? So then you have to say, okay, then the pen itself is going to push down, right, on the table, right? So then when you have the equation, what you are going to say is this is going to be the negative. Let's stick to the color sequence here. So the force is the pen on the table, right? So that's the pair, right? And again, each force acts on a different object, and they are kind of tugging on each other, right? So one does one, the other, so it's like a tug of war, right? If I push on you, you push on me, kind of thing, right? So because if you're talking about the weight, you're talking about the earth, right? So then that's the conversation you're having, pen and the earth. You can't have a conversation about the table, right? Because at least with Newton's third law, the focus is on those two objects. Now, if you are wanting to talk about the table, you're interested in the normal force, you want to measure it or something, you want to figure out how much force is the pen applying on the table, then this is what you want to do, right? You want to have this pair, not the earth pair. Does that make sense? Yeah. So it's a little subtle point, right? It takes a little getting used to because it seems quite easy, equal and opposite pairs, right? Every force has an equal and opposite pair. And don't take it too lightly. There's something a little bit more stricter definition and hiding in there. So you want to be really careful. It's both the forces you're talking about, one thing should apply on two different objects, right? So when you're talking about you sitting on a chair, if you're thinking about your weight and the chair pushing up on you, that's not the pair because both of those forces are acting on you, right? The weight is the earth pulling down on you. The normal force is the chair pushing up on you, right? But notice it's on you, on you, on you. Both those pairs of forces are on you, the object, right? So that can't be the pair, right? When you're trying to find the pair, each of the forces should be on a different object, right? It's acting on a different object. So that's one thing. The other thing is also just don't get confused by the different forces. Yes, there are different forces involved depending on what particular aspect of this are you focused on, right? Does that make sense? Okay, hopefully that's clear. Ask me any questions if that's not clear. How are you doing?
We had a question saying if there's an opposite and equal force, why do things break? If I hit a wood board and it breaks, why shouldn't the force of the wood on me be the same and therefore prevent it from breaking?
Right. So, yeah. So there is this limit to how much a material can push you back, right? So that's a good question, right? So if I take a piece of paper, right, and I pull on the piece of paper, or I try to have my friends hold the paper and I kind of push on it, right? There's a certain material strength that material has, right? So paper, not very strong. If you're talking about, I don't know, steel, right, something like that, pretty strong. Depending on the material, they have different strengths, right? That has to do with kind of how they're bonded, what kind of material they are, so that's a little bit more complicated. Roughly, bonding of the material, right? So atoms, how they're bonded together. Now, yeah, so at some point, the force you're applying will exceed that strength, and then things will break. But up to that point, you can still apply that force. So if you're applying a force on a piece of paper, it will push you back. So maybe you're gradually, right? So let's say you take a piece of paper and you're pulling on it, right? So if you're pulling on it, it will tug on you back, right? So same deal will apply. So if you're pulling, right? And you can feel it, right? So you can feel like if you grabbed it kind of lightly and you pull, it pulls back lightly. If you pull even harder, it pulls back even more. But there's a point where it won't be able to do that anymore and it'll just rip, right? But up to that point, this still applies, right? So until you break the material, so same thing with the table, right? So if you are doing kung fu or something, like you put the wooden blocks and you try to break it or something like that, you can do that up to the point it breaks, right? So you can keep pushing on material, and it will push you back by the same amount till you get to the point where there's a incredible amount of force on that material, and the material breaks. And at that point, of course, it can't push anything back on you, right, once it breaks, right? Yeah, that's a very good question. Go ahead, keep them coming. If you have questions, keep asking. Let's go and talk about a problem that involves all of Newton's laws. We're going to kind of put everything together, right? So this is kind of like a homework problem that you have. Let's say you have a situation where there are two blocks. M1, M2. If you're moving, think about having two moving boxes side by side, right? And you might push on these boxes with a certain force. And we may know that the mass of the first one is larger than the mass of the second one. And what we're trying to do is find the acceleration, first of all, of the whole thing. Right? And so what we're going to do always when we have a problem is kind of have a idea of what we mean by left and right, up and down, right? So we'll stick to the standard coordinate system here. And the question we're trying to answer for part A of this problem is, what is the acceleration of the system? And by the system, I mean both these blocks together, right? So the word system is used. What are we focusing on, right? We're focusing on these two objects. That's our system. Okay, so now you know kind of the method to do these sorts of things, right? Using Newton's laws, we always write down Newton's second law, right? The one for constant mass. That's what we're going to focus on in this class, right? You're aware of the non-constant mass case, right? The more general case where it involves momentum. We'll be back to that form a little bit later in the class when we talk about momentum again. So for now, F equals ma. We know there's only motion in the x, right? We're not applying the force to make the boxes go up or down. So all we have to do is focus on the summing of the forces in the x direction, which is mass times acceleration in the x direction, right? Okay, sum up all the forces in the x direction. There's only one, right? Just the force that's being applied. So we'll say plus F. It's in the positive direction. And that's equal to the mass, but it's the mass of the system, which is m1 plus m2 times the acceleration in the x direction. And then we can solve for it, right? So we can say the acceleration in the x direction is the force divided by m1 plus m2. Okay, so we have done the first part of the problem is to find out what the acceleration is of the system. Okay, so let's do the second part now. Okay, what we want to know is what is the magnitude of the contact force between the two blocks, right? So we're putting back our diagram. Here are the two blocks. The force we want is a force right here. Okay, now without Newton's laws, right, if you pause and just kind of said, okay, let me just guess what the answer is, right? You might guess the answer is the force, right, F. Because you're saying, look, there's a force here. I'm applying 100 newtons, something like that, onto the boxes. So then the force that's here in between the boxes should be just the force, right? That's the end of it, right? But here's why that something that seems kind of easy or clear is not that clear, right? It's actually, you want to be really careful. You don't want to just jump that to that conclusion, right? So let's see. Maybe it is, maybe it isn't, but we want to be really careful about thinking through that, right? So we're applying a force on this side of the system on M1, but what's the force between the two blocks here, right? So that's what we're after. So what I want you to do is draw free body diagrams of each of these, right? So just good practice for you. So let me put down M1, right? And then M2, the two blocks separately, right? And when we have two objects, we can draw two free body diagrams. We'll stick to the standard coordinate system, X and Y. It's always good to have that on the side just to see, keep a reference point, right? Okay, so draw free body diagrams for both of these, right? I'm going to pause for a second just to have you work on them because it's really critical to be able to draw free body diagrams yourself, right? And with a free body diagram, remember, only external forces to that object, right? M1, from the perspective of M1, what are all the forces pushing, pulling, right, on it, right? That's whatever acts on M1 externally goes onto the free body diagram. Same thing for M2, right? What's external to M2, what's acting on M2, right? So draw in the vectors for the forces, label them, right? Always good to label them. And as brownie points, you can post your diagrams onto Ed Discussion so then Jericho can see what you're kind of up to, what you're doing. So yeah, just practice this because it's really critical. If you draw your free body diagrams really well, this makes the problem-solving process much, much easier, right? So I want you to actively try this out because we'll do it together, but before we do that, make sure you can try this yourself. So let's pause for 2 minutes and we'll come back. Okay, so let's check on how you're doing, how we're doing. Get your free body diagrams. Jericho's not seeing yet, I don't think. Any on ed discussion? Post some. Don't be shy. It'll be good for everybody to see each other's work, right? Again, it doesn't have to be too artistic, and if it's incomplete, that's okay, right? The point is to see the thought process, right? When you all can see each other, what each other is thinking, right? That is useful for everybody, right? In terms of the learning process. Okay, what does it look like? We'll take a quick glance. Yeah, so see Sophie's one, normal, yeah, it looks good, right? So it got the forces for each, good, very good. Yeah, so that's what I mean, right? So draw free body diagrams, post it as we go. So do that so that people can see what everybody's up to, right? So that's a good way to think about this. Who's this by? Oh, Isabella's got one. Yeah, very good. Right, so good. So keep them coming. It's very good. Yeah, because when you're actively doing this stuff, you learn better, right? So yeah, you can see yourself being better at these problems as you kind of try this out for yourself, right? So let's think about M1. All the forces that apply to M1, well, there's that external force that we're applying on the left side, that's there, right? Then we have the weight, right? The Earth is pulling down on M1, right? So the weight of 1 is there. We have a normal force, right? The force that the surface, the ground is pushing up on M1, right? And then we have also a contact force, right? So we have a force that M2 is applying on M1, and we'll call that P. You can call it whatever you like, but I'll call it 2 on 1, right? The force that 2 applies on 1, right? So that's it, right? And when you draw a free body diagram, please pause for a second to see if you captured all the external forces, right? Because if you rush through this and you forgot the normal force, or you forgot the contact force, or you forgot one of the forces that's actually applied to M1, it won't give you the correct answer. It will really mess things up. And so because the free body diagram is your starting point, and then we'll write out F equals ma, and you'll go through the equations, it is extremely important you stop here, pause, and make sure this is correct, right? Because if the directions are correct, you capture all the forces, then your life is a lot easier, right? Because imagine you forgot this force, you worked through F equals ma, and that means you have to come back here, redraw your free body diagram, and work through F equals ma one more time, right? So take your time with your free body diagram, make sure it's complete, right? So that's good. That's all the forces acting on M1. So check your own diagram so you captured all of these, right? So M2, same deal. We have weight, right? So the Earth is pulling down on M2, weight of 2. Then we have the normal force off the surface again, right? So there is a normal force off the ground. Okay, and we have the contact force, right? So we have P1 on 2. Okay, and again, pause, see if you captured everything. Notice that that external force is not there, right? So this external force that's applied to the system, it's not in direct contact with M2, right? So therefore, it shouldn't be in the free body diagram of M2. Only forces that are directly, right, directly affecting M2 should be on the free body diagram of M2, right? So that's why F, that external force, is on M1 but not on M2, right? Okay, questions about the free body diagram, because that's really important. We'll talk about F equals ma in a second, but how are we doing on the free body diagram? Okay, good, yeah.
There's people are asking about if we're neglecting friction. I think someone's free body diagram even includes.
Oh yes, good point. Yeah, let's see. So just like we talked about for kinematics when we ignored air resistance, we're gonna when there's a surface. In reality, of course, there's friction, right? So in everyday life, the things you're dealing with will involve friction. We will talk about friction. We're not going to ignore it and completely not talk about it. We will talk about friction likely next time. We should be getting into friction next time. And so we'll talk about it, but for now, let's ignore it. It's a little bit more complicated to deal with when you add friction, just like in the case of air resistance, it makes things a little bit more complicated. But yeah, for now, ignore friction, and we'll bring it back later. Yeah, but that's a good point. Okay, so once you have the free body diagrams, what you want to do is apply F equals ma, right? So you kind of see the pattern of these problems, right? So you draw a free body diagram, and then you apply F equals ma. We always start with this, right? So sum of the forces equal to mass times acceleration. We think about how many equations do we need to pull out of this? Remember, even though we write it in this very nice compact form, it's actually 3 equations hiding in there, right? So for this case, this is 2-dimensional, right? The forces are acting in x and y. So we need to pull out the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. And we need to pull out that the sum of the forces in the y direction is equal to mass times acceleration in the y direction. Right? So you need 2 equations because the forces are in 2 dimensions. Okay? So which one do we want to focus on first? Let's focus on this one, fewer forces, right? So let's maybe it's easier to deal with. Let's focus on this first, right? And let's think about applying each of these, right? So we'll do this one first. Let's say y, right? Like we're going to do the y equation, sum up all the forces in the y, right? So sum up all the force in the y is equal to mass times acceleration in the y. And we'll say block 2, just to be clear, we're applying all of this to block 2. And if you sum the forces, right, sum of the forces, well, there's a positive normal force, there's a negative weight, and what's that equal to? Well, this isn't accelerating up or down, right? We're just pushing the boxes horizontally across the floor, so that's equal to 0, right? No acceleration in the y direction. So what that says is the normal force is equal to the weight. Okay, great, right? So we kind of, it's a bit clear, right? That's what should be, right? That for M2, the forces in the vertical direction should balance and cancel, right? And that's what this is saying, that the normal force and the weight for M2 are the same. Okay, that's probably clear from even not doing this F equals ma equation, but it's good to check, right? Okay, so then let's do it in the x direction. Sum of the forces in the x is equal to mass times acceleration in the x. We come back to block 2. How many forces do we have in the x direction? Just 1, right? So then we say positive P12 is equal to M2 acceleration in the x direction. Right? So just applying F equals ma to in the x direction for our block M2, that's what we get. We have 1 force, mass of the block, and the acceleration in the x direction, right? Now, one nice thing is we've already done this part, right? In the previous step, we already solved for the acceleration in the x direction, right? Because we said, what is the acceleration of the system? We already have that. But we need the acceleration of block 2, right? Because when we're saying we're applying F equals ma to block 2, the acceleration we're talking about is particularly focused on this block, M2. The point is that if you know the acceleration of the entire system, then M1 and M2 individually are also accelerating at this rate, right? Because if they're not accelerating at that system's rate, then they would spread apart, right? They wouldn't stay together. But if as a system it's accelerating in such a way, that means M2 is also accelerating in the same way, right? So that means we can use this to our advantage. So I'm going to move that over here, right? So I'm going to write that the acceleration in the x direction is equal to the force divided by m1 plus m2. Result from the earlier step we're going to use. So now what you can do is write that P12 is equal to m2 F divided by m1 plus m2, right? And to make it a little bit clearer, what you can say is, and move this around a little bit, if I move the m2 divided by m1 plus m2 times the force, now you can see this a little bit clearly, because now you can see and make a claim about the contact force. You can see the contact force is not equal to the force, right? Because there's this ratio, right? This fraction here. And by the fraction itself, you can tell which way does it go. Is it larger or smaller, right? Now, look at this fraction. Is it greater than 1, less than 1, equal to 1? Yeah, it's less than 1, right? It has to always be less than 1, right? Because m2 is at the numerator, the denominator will be a larger number, m2 plus m1, right? So the two together has to be larger than the thing on top, right? So then this will always be less than 1. And so if you're taking a fraction that's less than 1 and multiplying by some number, then the result will be always less than what you have with f, right? Whatever f is, P12 is smaller than f, always, right? So that's why I mentioned earlier, right? So you want to be really careful, because if you see a problem like this and say they ask you, what's the force right there? Don't just jump and say, well, that's just F, right? Because you might do that before learning Newton's laws. You might say, well, that seems to be the obvious answer, but the obvious answer is not always correct, right? So you want to be very careful. So if you see a situation like this, always good to go through the Newton's laws applications, right? And then if it turned out the two forces are the same, great, okay, fine, that's okay. But in this particular case, the two forces are not the same, right? Well, the contact force is less than the force you applied. Is that okay? Doing okay? Ask us if something's not clear. Happy to go over it. I want to kind of get a sense of how everybody's feeling about Newton's laws, kind of comfortable with it. If it's not in the process of solving these questions or what's not clear, we can do another practice problem. We'll work through another problem so you get more experience working through this, right? So hopefully it's becoming clearer and less confusing, hopefully. But if something is confusing, don't hesitate, ask.
There's some confusion on the last part. There's just like we're pulling that F equals ma from the total system and being able to plug it back in to the.
Oh, the acceleration?
Yeah.
Oh, yeah, that's good. So hopefully, like, this part of going through the free body diagram to the F equals ma that associated with that particular free body diagram, that part's okay. If that's not okay, let us know, right? So the point is you can draw two free body diagrams. We drew a free body diagram for M1, but we didn't really use it, right? You'll see that what we did was just use the free body diagram for M2. You don't want to skip the step, right? Initially, when you're starting off, it's always good to draw as many free body diagrams as you can think of, because there's two objects, draw two free body diagrams, right? And also, you can draw a free body diagram of the system together. M1 and M2 together could be another, so you can potentially draw three free body diagrams, right? So draw free body diagrams, don't hesitate to draw them, right, just for practice. But then once you have the free body diagrams, each free body diagram gets its own application of F equals ma, and don't forget, F equals ma is in x and y, right, x and y. Right, so each one you can apply F equals ma in 2 dimensions, right, in this particular case, right, it's two-dimensional. Once we applied that, right, once we applied this, we take this free body diagram, we apply F equals ma to that free body diagram, the acceleration we're talking about is the acceleration of m2, right? When we say mass times acceleration, we mean the acceleration of the m2, right? What is this acceleration? Up to this point, we just keep it as a variable. We don't know what that is, right? But then coming here, we actually do know what this is, right? And we know it because we solve for the acceleration earlier in this problem, right? We had the system and we said, okay, what is the acceleration of the system? So when I copied over this result, I'm just copying that value, right? So I'm copying this from here. And the logic here is that this is the acceleration of the entire system, right? Both blocks going together, that is his acceleration. But if I ask the question of, okay, fine, but what is the acceleration of m1? What is the acceleration of m2, right? It also has to be this number, because if they're not accelerating together, right, then they would spread apart, for instance, right? So imagine m2 had a much larger acceleration than the system, then it would come apart, right? So that's the claim, is they're not going to come apart. When you're pushing the two blocks across, they're going to stay together as a system. And so whatever acceleration the system has, then m2 must also have that acceleration, right? And that's why that allows me to copy that over and said, aha, okay, I know this information from earlier. Why don't I go ahead and use that, right, information? And that helps you get to this conclusion, right, that you can make a claim about what the force is doing, the contact force. Okay, let's set up another problem and get you more practice with applying Newton's laws, hopefully getting more familiar with them. Okay, let's look at this scenario where you are trying to hang something from, let's say, your ceiling. And last time we did something similar. We didn't know what the weight was, but in this case we do know the weight. And so you're hanging this. There's some cords. Okay. And each of the cords has a tension, T1, T2, T3, right? The force that's applied, right? So the force that's going through the cord for each of them. We know that the weight of this is 122 newtons. And we know a few things about the angles. We know this is 37 degrees, this is 53 degrees. And what we are trying to find out is, will cords 1 and 2 break? Okay, so if you're designing something, this is a question you have to think about, right? If you can't just hang any weight off of any cord, right? At some point, it's too much, it'll break. So we need to see if these two will break. And if tension 1 or tension 2 exceeds 100 newtons, they will break. Right? That's the material, right? So maybe it's made out of a certain material that if you pull it on it too much, it'll break, right? Okay, so we're not going to worry about tension 3. Imagine it's made out of different material. Maybe it's made out of titanium or something, right? It's made out of something else. We're not worried about that. We're worried about tension 1 and 2. That's what we're concerned about. Those are the ones that can potentially break, right? So that's what we're going to do. Okay, so pause here, think about free body diagrams. Okay, this is the diagram of the setup, right? Because this is what kind of would look like if you saw this in real life, right? This is what it would look like. But you want to make it a little bit more abstract by going into the free body diagrams. So how many free body diagrams could you possibly draw here? 3 here. What are the 3?
T1's free body diagram, T2's free body diagram, and the weight.
I see. Yeah, so you're trying to draw a free body diagram of the chord itself. Possibly, I see what you might be saying. Yeah, you can, because the chord is an object in itself. You could potentially draw a free body diagram of that, right? So try it, right? What else? You said the weight, you can draw a free body diagram of, right? So you can focus on this and draw a free body diagram of that, right? What else can you draw a free body diagram of? Yeah, so all the chords, and then what else? So the 3 chords are there, but the weight is there. Well, there's maybe something that's maybe less obvious that you can draw a free body diagram of. Yeah, the node, right? So when you see something like this, yes, you can draw a free body diagram of maybe the chords themselves, but try to focus on objects and nodes, right? Generally, nodes are important, right? Because why? Because if you make a free body diagram of the nodes, you have to put all these 3 forces involved, right? You get them all involved. So nodes are less obvious because you might focus on the objects, which is expected, right? You see the objects and you say, I want to draw a free body diagram of that. That's clear. But nodes, don't ignore the nodes, right? Okay, so free body diagram number 1. Let's take it on the weight, right? And it doesn't have to be very fancy. The weight itself can be modeled as a dot, right? That's okay. It doesn't have to take a shape. I'm going to have the XY coordinate system centered on the weight, and I'm going to put all the forces that are acting on the weight, right? So upward on the weight is tension 3, right? That tension is pulling up on the weight. And what else is acting on the weight? Well, gravity, right? The Earth itself, right? There's a force due to gravity pulling down on the weight. Those are the 2 forces, right? Those are the only 2 forces acting on the weight, right? So that's it for this free body diagram. And we'll draw another free body diagram. There's free body diagram number 2. Again, the node itself I'm just going to represent with a dot. Okay, and always have in mind where your X and Y are going, right? Don't want to forget that. And now we can put in the forces. Tension 3 is pulling down on the node. What else is there? Well, there's tension 2, kind of at a diagonal, that's tension 2. And then there's tension 1, right? It's kind of going this way. All right, so hopefully you're kind of seeing that, right? This is how you translate, right? So you take this problem, you're trying to draw free body diagrams. I've taken the node and I put all the forces external to the node that's acting on the node, right? And I can also now put in some angles, right? So here's the 37 degrees by using that method we talked about earlier, the trig identity. We can say this is 37 degrees, right? Because once I know this is 37 degrees, this line is parallel to my x-axis that I'm drawing, right? So essentially I have that Z pattern, right? So I have a Z where it looks like this, right? Well, it's kind of an opposite of a Z, but you get the idea, right? So it's a shape, so you have this shape, right? So that is there. And so when I have that shape, this angle and this angle that's interior is the same, right? That's still 37 degrees, so that's why I'm copying that over here. Same thing with the 53 degrees, right? So this will also be 53 degrees. Why? Well, draw a parallel line to the ceiling, right? And if that's 53 degrees, then what's right here, right? This angle right here is also 53 degrees, right? A little trig identity there. Okay, so we're at the end of the class, so we're going to pause here, right, at our free body diagrams. We'll continue with this problem next time and more on Newton's laws. We'll talk about friction, right? Somebody asked about that. Like I said, more about the exam coming to you through an announcement today, so pay attention to your Canvas announcements, and I'll tell you more about what to expect. Mostly, I think, got honor lock sorted out. I think for those of you still having issues with honor lock, we'll work with you. Make sure you get another chance to practice just trial running honor lock, making sure the whole thing works to you before we get to Tuesday. All right, we'll stop here. We'll see you tomorrow.